So, okay, let me start with introduction of our team. It actually started all here on this meetup. It was Bruce's idea to start the competition with beginners who never done Kaggle competition before. So that's including me and Andy, Eva, and Adrian and Ellen, who couldn't be here today. And yeah, let's start with the competition. The whole purpose was to help monitoring ship traffic, and it was held by Airbus, which provided satellite pictures of sea. There are a few samples. As you can see, there are pictures with a lot of ships. I think maximum was something about 15, and there were also a lot of pictures with no ships at all. The task of the competition was to, for each image, detect all the ships on the image, and for each ship, produce a mask which would basically label all the pixels with the ship. This is a ship, and everything that's not ship, it would be like basically value 0, like there is no ship. And then submit CSV with all these masks. The questions?
I was just wondering if you could be a bit more specific by what they mean by ships. Does that include boats and yachts and things like that, or is it just like container ships and battleships and really large vessels?
Okay, I believe there were small ships as well. There were not just the tankers. I'm not sure about it. But yeah, there were like more types of ships and not just the big ones. Okay. So quickly about the competition. There was $60,000 prize money and about 900 teams. And we finished, as you can see, at the top 75%, which is quite good, I would say. Okay, our score was 0.78, and the score of the first team was 0.85. Yeah, which is quite good. So, as I said, we were given images. There were 75H times 75H pixels each, and we were given 190,000 train images. These were labeled, saying like which pixel is ship and which is not. And then we were given 15,000 test images for which we were supposed to generate masks, basically. So, okay.
Do you have any idea how those training images were labeled? Did the competition say?
They didn't say it exactly. I think there were some discussions about it in the forums, but I don't know from the top of my head. Yeah.
Okay.
Any of you? Oh, okay.
You think it's 192,000? No. So that's probably another model that was training the. Yeah, that's a weird. It seems like weird.
Okay. So with the train and test images, we were given also train ship segmentation CSV. It had basically two columns. One was with image IDs, and second one was run length encoding of the mask. And as you can see, there were basically three options: whether the image had like no value for encoded pixels, that basically meant there were no ships at all on the image. If for one image ID there was just one line, it meant there was just one ship, and then there were images which had more lines, and that meant there were more ships. So yeah, sorry. How the run length, what did that mean? What that meant? Oh, sorry, I just wanted to. Okay, so it was also pair of two numbers. First number in the red rectangle was basically position of the pixel with the ship on it, and the second number was the amount of pixels that are labeled as a ship. So there were like 750 times 750 pixels. It was something about, I don't remember now, but yeah. So basically, the first number says like pixel on the position, blah blah blah, is ship, and so on, so on. So after decoding the masks, we were able to see and overlay it with the train images. I picked 3 random images, as you could see. This one has just one ship. That's the mask for it, which was generated from the CSV that I showed you before, and that's the overlay of these two. This one has 2 ships, and this one has 4 ships. So the whole train set was quite unbalanced, I would say. There were much more images with just the sea, with no ships on them. So actually 150,000. So most of the teams, what they did, my colleagues will talk about it later, I guess. But what they did, they basically trained their model on just the images with the ships, because for determining whether it was an image with ship or with no ships, they used different model, which was basically just the ship classifier with quite high accuracy. It was something about 98%. So basically, most of the teams, they just, as a first step, they decided whether there is a ship on the image or not, and after that, they labeled the pixels.
Okay, so what was the evaluation metric? So for the evaluation metric, we use the F2 score and the intersection over union. I know that usually the intersection over union is calculated on the whole image. In this case, we just calculate for every SIP or every prediction. Intersection over union is basically the ratio of intersection over union. And in this case, in the formula that I have over there, A is whatever we predict, the set of the pixels that we predict, and B is an actual SIP that exists there. So we run the F2 score over different thresholds, and the thresholds go from 0.5 to 0.95, and they just increase by 0.05 every time. So we have just 10 different values of the threshold. And basically every time, because I know many people know that, but there are also some people that might not know that. But like, we say that a prediction is good enough if based on a given threshold, the intersection over union is bigger than this threshold. So if, for example, we're looking at threshold 0.6, if the ratio of intersection over union is bigger than 0.6, we have a hit, we have a good prediction there. So again, we run the F2 score over the different thresholds. So for each image, we calculate this formula over there for each image and for its threshold. And by TP, we mean the number of true positives. So all the predictions that are actually good based on the threshold that we are looking at. Fn are all the false negatives. So every time that there is there is a SIP there that we didn't give a prediction about for that SIP. And FP is all the false positives. So every time that we gave a prediction and there was no SIP or there was not enough SIP in this prediction. It is a little tricky when you have images that they don't have any SIPs at all. If there are no SIPs and you give a prediction, based on the formula that you have over there, TP is gonna be 0. And then at the denominator, you have TP0, FP is gonna be 0 again, and FN is 1 or something bigger than that based on how many predictions you gave. So this will give a score of 0. On the other side, if you have no SIPs at all and you make no predictions, this formula will give you 0.0 over 0. So we will just define this to be a score of 1. You made a good prediction, no SIPs. There are no SIPs over there. And then for each image, we want to take the average of all the F2 that we have calculated for its T, and then the final score that you returned for the competition is the average of all the averages F2. And I think this is Andy.
Hello? 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 Hello there. It's working? Okay. Can you hear me at the back? No? Maybe I... Did you rewind on? Oh, weird. Why is it not working? Here, let's see this.
Is the evaluation metric calculated per image or per prediction?
Per image.
Right, so you're combining all of the masks for each different, where an image has multiple predicted ships.
So you mean the final score, whatever you give at the end? Or like the F2 score?
Yeah, so you've kind of suggested it goes both ways. You've suggested that you would calculate the intersection score
Yeah,
per
so the
image,
intersection
or
score
one
is going to
per
be for
prediction?
each SIP or its prediction, and then you take for each image you take the F2 score, and then you combine all this by taking the averages of all this.
Hi. I want to clarify, this task is a object segmentation task, instance segmentation task. So for each ship, we have the ground truth mask. Let's say one image has like multiple ship, then we have like multiple mask ground truth. And now I'm going to talk about how do we learn the mask. I see lots of expert here, and I'm probably not the perfect person to teach or talk about these two things here. I have some research experience in machine learning, but not so much in neural network. So that's what I learned in the past 3 weeks, and I'm going to talk about it. So there's two state-of-the-art method. One is called UNet, and one is mask FastCNN. I'll talk about UNet first. Just want to know, everyone aware of, if someone knows CNN really well, please raise their hand. Then if someone like aware of it, then please raise your hand. Sure, okay. I guess I need to go over what is CNN first. So CNN is convolutional neural network. Next slide. So it's basically some neural network stacked together to extract information from an image. And to explain it, probably use the next slide. So the key idea in convolution is do a convolution plus polling. So you have a fixed filter, or I can say kernel, and there's some weights on it. And then the green thing is the filter, and the blue thing is the image. And we will learn the green thing by kind of scan through the image. And that's the idea of convolution. Yeah, you can correct me.
Yeah.
So the bottom thing is the image.
Oh, sorry. The kernel or the filter is the 3x3 block at the bottom. It's like in a dark blue. And then the green thing is the output of the convolutional layer. And now I'm going to talk about, I first will give an example of a typical convolutional neural network. Is by stacking this layer one by one. So you have a really high resolution image, and then you will stack this layer. And then at the end, you get a small patch that will kind of like the feature of your image. And with UNet, the idea of UNet is you first kind of downsample your image by go through some convolutional layers, and then you do an upsample with some other convolutional layers. And also there's a great line here that the idea was that the information from this side will go to this side by a concatenation. So you can imagine this is your image, and then when you go through the network, it will lose lots of information, and then you will do a upsampling to kind of extract the information from here, but also plus some information coming back in this side of the network. And also I'm going to talk about what is up convolution, or the upsampling on this side.
So if you go back to the UNet, so the downsampling makes sense to me, although how exactly are they doing the upsampling, or are they just blowing up the image?
That's what I'm going to talk about soon.
Whoops.
Yeah. So this is a downsampling. So this is the original image. The 3x3 is the kernel, and this is the output. The green one is the output. And with the upsampling, you can see the 3x3 is the filter or the kernel. And then with this little patch here, and then with a kernel, you can have a higher resolution kind of feature if you do this operation here. And also here, that's how they do the concatenation. They use the feature on the downsampling side, and they just concatenate, with the feature here on the upsampling side. And why we need to do this concatenation copying is because when you do the down convolution here, you always lose the border pixels. And let me go back to the U thing. So this architecture is called UNet because it looks like a U, and is usually for segmentation. Because with typical convolutional neural network, it's usually used to classify. Usually used as a classifier, but in segmentation, we need a really high resolution solution for each pixel, and I think that's how they come up with a upsampling, a up convolution thing. And next, I'm gonna briefly talk about FastCNN. And to talk about FastCNN, there's a couple paper to reference here. And the first ideas are CNN. So the idea was that to do segmentation, you first propose some object proposal in the original image. So is this stage here, you have the original image, and then you use some traditional vision algorithm to propose some region. And that region is saying that there might be some object in this image. And usually there are lots of many proposals, it's up about like 2,000. And this is using traditional vision algorithm, is based on like signal processing. And then you will process this little region. You will throw it into a convolutional neural network. And then after it got through the convolutional neural network, it has a SVM to classify the regions to predict its category, and also have a bounding box regression. And this bounding box regression will kind of fix the bounding box, the region you propose here, and then it will have a it will learn it. The loss function will be the combination of these two loss.
I studied this in school, and I remember learning some stuff that I'm hoping that you can kind of confirm or tell me that I'm forgetting it wrong. So in your slides, you're going to be going through this in order, right? Like RCNN came first, and then came FastCNN, and then came faster CNN, and then like, so there's like you're gonna be kind of building up on each other, kind of as you're going through these. So one of the reasons I remember why RCNN wasn't very good is that these SVMs are trained independently from the deep learning model here. And so you kind of have to do them in two different training steps, and you don't really have end-to-end training in this. Okay. Is that?
Yeah, I think
sound right? Okay.
That's correct, yeah.
A big thing with RCNN is that it's really slow, and that's because like with every single like spot you have to go through the network itself. So you're basically dealing with like thousands and thousands of iterations going through your network, whereas like the later ones you're only dealing with like going through it like once or even then. So that's kind of like what I guess he'll go over that, but yeah, that's the main reason why they improved on it.
Are you familiar with all of these, like past RCNN, faster?
Decently, yeah.
Decently? Okay, maybe if anybody else is familiar as well, maybe we can kind of just talk about the pros and cons of each one of these as we go through it, because I think that's like important how they progress.
Yep. So the next one is FastCNN. Like I mentioned in the RCNN, for each image, they have around 2,000 proposals, and then they will feed each of them into the network. And that's very expensive. So what they do is they first put the whole image into a neural network, and then they will kind of extract the region of interest from this feature. The feature is what the image, what the output of the convolutional neural network. And then they will do a polling layer. The idea is kind of similar to CNN. And then the rest is pretty similar, except this classifier is just a linear plus softmax classifier. And the whole idea why it's faster is like the gentleman mentioned, is only pass one image into, for one image only pass the whole image into the convolutional neural network.
Hey, there we go. So with this ROI pooling layer, there's going to be a fixed amount, I would assume, of ROIs. Is that correct?
Fixed amount of ROI. I'm not sure. It's not. I think it's not a fixed amount of ROI.
I don't think so.
Oh, it's just because it goes into that fully connected, which needs to be.
I should probably mention, so for a fixed CNN, the image you feed into or some feature you feed into, it has to be fixed dimension. And so in here, they kind of warp it, I think that's what they warp this region into this size. So you can see in here, this 3 region is not in the same dimension. But in here, before it feed into the fully connected layer after, is the same dimension.
No, you're onto something. You need to figure that out. I don't know.
He doesn't know.
I was talking to the mic, but so what feeds into the fully connected layer? Just one region of interest at a time?
So what are... I can't remember exactly, but I think it's basically it finds like a certain amount of regions of interest. Like it goes through the network and then output is like multiple regions of interest, not a fixed amount, but I'm not 100% sure on that.
Okay.
Yeah.
But then is to echo Matt's question, what is the input into the fully connected layer? Is it all of these different regions of input? And if it's a whole bunch of different regions of input, then because that fully connected layer has a certain size, right? Yeah. So it shouldn't be able to take a dynamic amount of region of interests.
I think it might go... I can't.
Okay. Look it up, guys, if you're interested. Do you have an answer? On the bottom? Look for the light.
Hello. Yeah.
Yeah. There you go.
I think maybe he mentioned like 2K, 2,000 proposal. That's the number of the ROI, I guess.
That was the previous model. Yeah, that was.
Oh, okay.
Yeah,
And
previous.
this one. So I have a question about the proposal method. About is it kind of randomly generated any shapes of the ROI? No.
No, so the algorithm FastCNN use is kind of traditional vision algorithm. I didn't look that up what that exactly is, but it's using some signal processing. So there's some algorithm to just propose some possible objects in the image. And for the question here, so this fully connected layer is kind of like it will learn the connection between a proposal and what after this fully connected layer. So they have fixed dimension and they have multiple proposals. It's kind of like you have multiple image for a typical CNN to train a CNN. So next is the faster FastCNN. And in here, the main idea of faster FastCNN is it will use a neural network to propose the proposal. And they call this neural network RPN, Region Proposal Networks. And there's some other details, but I didn't put them in slides, so I'm not gonna mention them. And that's the key idea is this, they use a neural network to propose the regions. And after this is the mask FastCNN. It looks pretty similar to FastCNN and the faster and the fast one. And in this side, before this red line is quite similar to faster FastCNN. But in here, they put another convolutional layer, and then they can predict the mask for each classes. And how they train this network is use a multi-class loss. So here they'll combine these 3 loss all together, and then they will train the whole thing. Instead of in the FastCNN, they will train the SVM. And then train the network.
Did you use these in the competition?
Yes.
Yeah? Are there, like, if you're just starting out, are there pre-built models that are pretty easy to implement?
Yes. Because there's lots of detail here, and they're a really good implementation on GitHub.
Yeah, there's excuse me. There's a couple of really nice open source implementations. The one we looked at was from Matterport, and they have pre-trained models there. It's really very well set up. They give you something that works right out of the box, and they tell you how to customize it and train your own data and all sorts of good stuff. So look for Matterport or Mask RCNN if you want to get into it.
Okay. I have one more question. Sorry. How long would it take you to get something going, like given a data set and like from the whole process of finding the resource and getting it to work?
So we found a kernel, a mass RCNN kernel, and to do everything end to end, and using one of the really good open source implementation of mass RCNN. And running that kernel probably spent me like 2 or 3 days. But I need to like understand this stuff. Probably I spend another week or so.
Not a question, just to add, TensorFlow also has an object detection API which you can use. That's pretty straightforward. You don't really need to know anything about how to use them. You just have to set up a config file properly. So yeah, that's another resource for you if you want to use that.
Yeah, I was just curious, how does the model deal with overlapping bounding boxes? If you have 2 ships side by side, what do you get out of it? Do you get 1 bounding box, or do you get 2 overlapping?
In this case, not quite sure the original mass RCNN will do on this case, but on the different solutions, there are different tricks to do that. One trick I saw was kind of using a 3-class classifier. So one class is for the background, and one class is for the ships, and then they have another class is for a contour. So it's kind of like if you have like 2 ships sticking really close together, they will predict kind of like a line between them, and then you will process that. Yeah. And also there's another algorithm I will mention later.
For mask RCNN, it looks like part of the way one would recognize a ship in these pictures is by looking at the pattern of water around the ship. So the mask would cut off that part of the picture. So wouldn't mask RCNN and similar CNNs be at a disadvantage because it just focuses on the part that has the ship without the water around it?
So they have I think the question about if you propose a region, it will somehow cut off the ships. And that's what they have here. They have a bouncing box regressor. So if you see, even in the fast RCNN, they have a bouncing box regressor. So they will penalize that. But I'm not quite sure the detail of how they penalize that.
I'm not asking about whether the ship itself will be cut off, but at the stage where when you're deciding whether the mask is for a ship or not for a ship, you have lost the information of what is around that part of the picture. For example, the churning water when the ship is moving, that part will not be part of the picture masked by the mask that was predicted. So wouldn't this put these approaches at a disadvantage?
I'm not quite sure what the question is, but I think the input of the whole network is an image. So for an image, the ground truth mask is fixed for each trained image. Lagrange math is fixed.
From my understanding, is like the region proposal network, which is trying to find the areas that the ships are in, would use that kind of information. But once like you're actually kind of like tuned in and like kind of focusing on that smaller region, then like when you're like these object detectioners, like they're kind of taking the whole thing and trying to find small things in it that will kind of the features that will kind of fire off like, okay, that is something that we're interested in. So like those, yeah, the water around it will probably help the region proposal, but like once it's actually kind of focused in, then like it wants to be able to separate that the churning water from the boat itself.
Just to comment, I think someone said earlier something about mask RCNN and overlapping and so on. So just to clarify, mask RCNN can detect both different instances of the same type of object and distinguish those, and overlapping objects. It's kind of miraculous, actually, when you see it for the first time, how good it is. I think, however, in the competition, and Andy's probably going to say more about this, its ability to distinguish two ships that are really close together is not enough, and you need to do other tricks to make that work.
Yeah, so mass RCNN is using like a region proposal based method, so it can solve that problem, solve some ship stayed together problem somehow. But in UNet, it's kind of like the output of the whole UNet is a high resolution mask, and it won't solve that problem as good as the mass RCNN. And there's some detail here about ROI, the region of interest alignment. So in the fast and faster RCNN, they use a ROI polling. And I can give an example over this picture here. So let's say this picture is 800 by 800. And then after it the whole picture is 800 by 800. After it go through a CNN, the feature will be shrink. Let's say it's become 32 by 32. So divided by 25. But the region of interest is like 110. And you use 110 divided by 25, you cannot get an integer. But what you want is the coordinate of the features. So the result become I want pixel 1.2 to pixel 3.1, and what that exactly is. So what they do in the fast and faster RCNN, they use a pooling, and they will just quantize this. So let's say you have a 1.1, it would just use 1. And in mass RCNN, this is one big improvement for mass RCNN. They use a non-quantized method to fix this problem. So if you think about it, in the layer that the input and output has high resolution, this quantized error may be just a little bit off. But when you shrink it and then you do upsampling again, if you get like 0.5 errors, and when you do the upsampling, it will maybe become like 30 pixels. And in some ships, they only take maybe like 50 pixels, and then you have like 30 pixels error, then that's a huge error. So that's one of the advantage of using mass RCNN over the RCNN method before. They use something called bilinear interpolation to avoid doing the quantization. And I want to again mention for fast and faster RCNN, they are not solely used for segmentation. And one reason using the ROI alignment is a huge improvement over the polling is that the task itself is segmentation. and you want a pixel precision mask prediction. And I'll talk about our solution. Our solution is based on mass RCNN with Kaggle pre-trained weight. Kaggle is a Microsoft segmentation database. So they have a image and they have this the segmentation mask grand truth. It's a pretty popular database for a segmentation task. And the mask RCNN is pre-trained on it, so you have the weight. And our solution is based on a open kernel. But that kernel only can run on the Kaggle kernel, which you can only train for, I think, for 6 hours. And then I modify a little bit so we can run it on Bruce GPU. And it's based on a really good open source mass RCNN implementation. And it will handle something like how you do the run length encoding and decoding. And it will let you define the number of classes. So in our case, it would be just 2 classes. And also let you define the image dimension, and it will resize it for you. And the backbone I use is ResNet 50, because I think that's the only ResNet model in Keras, built-in Keras. And I wish I could switch to like ResNet 101 something, but just easier to use 50. And also I tweaked a little bit about the learning rate, and I implemented the learning would drop after some epochs. And this is kind of the result of our solution. So the number here is the prediction score. And this side is the grand truth. So you can see so this one I think is an island. And it looks really like ship on a satellite image. And I'll hand it to Eva to talk about some method other teams do.
So yeah, here are some of the loss functions that people used for the competition. So loss functions are used in general to kind of like see how well the model behaves. And my understanding is that you take these functions and you run them through some optimization method, and then you just want to have an error as small as possible. Why they helped in this specific competition, in the sense like why were they helpful to distinguish if they were like 2 SIPs very close to each other? People mentioned that like they helped so that you will be able to distinguish these 2 SIPs, or to just have better masks for SIPs and stuff like that. For that, I'm not sure if I understand that very well. So if there's anybody here that knows why the functions, the loss functions would help with that, please. Is there?
So I think the reason why you have to use these loss functions here is that the score itself, that intersection over union, because it's like a discrete measure, you can actually take the derivative of it. And if you can't take the derivative, you can't train the neural net. So there needs to be some approximation of what you're trying to find, that overall like loss function, and you use something like cross entropy loss, which we'll go into.
So this is, in general, every time that you want to make an optimization, you want to have a differentiable function, right? So, but like, why specifically does it help with like distinguish the SIPs, or like that's?
So if you were to say if you could try to optimize that score, the intersection over union, which is a very complex function you're trying to optimize, it might be not very stable, and that would really hurt training. So you're trying to find something that's relatively smooth, and I know smooth and differentiable aren't the same thing, but in this case, that's all you really need to know is you want the model to be able to figure out if it's going in the right direction as easy as possible. And something like cross-entropy loss would be a good case, but there are definite weaknesses that you'll go into.
Yeah, I have some other ones later too, and it's kind of like the same as you're talking about.
You want to try?
Well, yeah, just to comment, I don't think this cross-entropy loss is going to help distinguish ships. It's really going to tell you for every pixel, is this a ship pixel or is this not a ship pixel, essentially. And the task of grouping those pixels into ships and separating clumps of pixels into different ships would be a separate stage afterwards.
Okay. Sweet. So as Matt, is your name Matt? So as Matt said, this is not usually enough, and this was the case in this competition too. People seem to use other tools as well besides that, exactly because the data set was quite unbalanced, as Adam mentioned. So another kind of thing that they tried to use is the dice loss function, which is very similar to intersection over union. The only difference is that there is these two in the beginning. And again, Matt said that this is not a continuous function, so you cannot optimize it with mathematical tools. So basically, you just want to take a continuous version of this function and make it as a dice loss function. So this is what we have there at the, this part is a modification of the dice coefficient. And again, this by itself is not enough because it doesn't give a very good training easily. So what people seem to do a lot was to combine these two together. Two combinations that I happen to see from some comments were these two. One of them was to just take the binary cross entropy and minus the logarithm of the dice loss, and the other one plus binary cross entropy minus dice loss. Another one that was mentioned by someone that did the competition was the focal loss function, which is very, very similar to the cross entropy. The only difference is that you add these factors that I have there with green. But other than that, is pretty much it's very similar to BCE. And the little gamma that we have there at the power is just another parameter that you add to the model. This person that mentioned that said that he used, I think, something that was very close to 2. I don't know exactly why, but yeah, that was the parameter that he used. And I think it's you.
I'll talk about the template solution, and is using MassRCNN. And our solution is based on MassRCNN. And one of the biggest reasons I think that we didn't rank that high is because we just use a straight MassRCNN, and we didn't use any ensembles. So one of the good solution will be like I use one model use UNet, one model use MassRCNN with ResNet 50, another one ResNet 101, and then I ensemble them together. So I think that's the main reason. Until I see this solution, it's like they don't have any ensembles as well, but they do have some tricks. So one trick is they use ResNet 101, which I didn't include. Another trick is they use a multi-scale training. So to detect some ships that are really small, and they will rescale their image. I think the ratio is really, really huge. Is that they will rescale it by 2,000 ratio. And then sometimes they will just crop a small region to train the model. and that's to how to solve some small objects, small ships. And also they include a algorithm to select top 125 ROI for the training. For this, the reason behind this, I could not, like, I just don't understand this. So they have less ROI for training instead of so let's say for one image you have 2,000 proposals, and they use a good algorithm to sort it, and they pick the top 128. Another thing is an algorithm to kind of remove the repeated detection box. So let's say you have two ships stay together, and it's like that, 45 degree. And then maybe the one in front is got like 0.9 score, and the one behind got like 0.05 score. And then in this algorithm, they will penalize on the overlap. And the original algorithm is penalize the overlap between these two bounding boxes. But they change a little bit, so they just penalize on the overlap between these two masks.
I'm trying to understand how the multi-scale training will help with small object detection. Because if you're increasing your small objects during training, that's to me going to make it even more difficult to find them in the test set because it's not used to seeing small boats. So do you know if they also upscaled the testing data when it came to test time? And then maybe kind of, because you could take one image and you can, scale it up by 4, and then you can just put those 4 regions together, maybe something like that.
Not sure.
I think the short answer is yes.
Yes to what I said.
Yes.
All right. Anybody disagree?
I think this is just like a data augmentation thing where you're just trying to generate more samples. At test time, I'd like, you could. I don't know if they did.
I think the idea is that they have lots of different images scaled up to lots of different factors. So like, let's say you've got 4, then you've got the image of the boat at 4 different scales. And on one of them, on one of the scales, it's very likely that it's going to look very similar to boats, larger boats, for instance, at a smaller scale. So it might pay attention more to that part of the input and be able to use the same sort of
Training time? Totally. I get it. Totally good at training time.
well, you still got you can still do the same sort of scaling at test time, right? If you automatically.
That's tricky.
I don't think you should.
No.
I think they only do it on training time.
Yeah, I take it back. I don't think you should do it at test. Just because this is a segmentation problem, and you're going to have to go pixel by pixel and decide yes, no, yes, no. I think that this is especially useful doing this hard example mining because let's go back to that island example that you had a positive on, right? So in training, you'd be able to find that in the hard example mining is trying to find the things that your model's like having the hardest time with. So you would want an example of that island at the current shape and size, but you would also want that island in a bunch of different sizes because hopefully that will generalize more deeply. So I think that all of these things kind of have like a multiplicative effect, and that's why they're 10th place. Does that make sense?
That's the augmentation.
Yeah.
So they just use the augmentation, the scale-based augmentation more than my model.
Okay. I think we can move on from this. Yeah.
So another solution that we'll see was the one that took the 6th place. and the score was 0.852, blah, blah, blah. And so they tried a bunch of different things. They first used the model that had a SIP, no SIP classifier. We mentioned at the beginning too that was very important, especially because there were so many pictures that had no SIPs at all. And they used Inception ResNet v2 trained on pictures of 299 times 299. And then the next thing that they tried was a unit with ResNet 34. And then again, they cropped the pictures. And then these people used, on the training set, they used about the same amount of pictures that had SIPs and pictures that didn't have SIPs, was kind of different than what other people did. Other people kind of concentrated on using mostly pictures that had SIPs. And then the performance was not that much better. From 0.846 took them to 0.848. And another thing that they used was again UNet with ResNet 152. Again, cropped the pictures, and this time they used mostly pictures that had SIPs in the buds. Just 10% of them was pictures that didn't have SIPs, and the performance was much better. Well, I mean, the final result was 0.848, so it was not like extremely better, but I mean, the difference was better. And then the other thing, another thing that they used was mask FastCNN with ResNet 18 or ResNet 50. And it took them from 0.843 to 0.85. At the end, what they finally did was to take 7 UNet models and 3 mask FastCNN models. And as Andy mentioned, it was very important to take an ensemble of many different models, and this is what these people did. The fourth place solution, again, these people concentrated on a classifier for SIP, no SIP. That was again very important. They used, for the validation, they used 9,000 images and mostly images with SIPs. Not that many images with no SIPs. They used UNet with ResNet 34. And they used binary cross entropy. And yeah, they didn't mention more than that. It was just that. And the person that won the third place, they didn't really mention what the model was. They just said that they took a model that they used from a Seoul classification competition. I don't know if you have seen that, but they just took this model and that they did some like minor modifications and they just used that. So some advice that I kind of like took from them, it's kind of like goes hand in hand with the slides later. It's very good if you have a team. It's great. Of course, if you do something by yourself, it's going to be much harder. This person said that they read papers every day on data science, and especially every time that they have a competition, they might read more than 100 papers. I did that never. I don't know if any of you have done that before. And the last one is completely random. It's just a reminder. They did some physical exercises, healthy mind in healthy body. I just thought of just mentioning that. And seriously though, lessons that we learned as first time, as forming a team for the first time. I don't know if there are people here that have never done any competition before. Just two? Okay. Perfect. The learning curve is steep, not very weird, I'm assuming. One of the best things that I learned was that you never want to start from scratch, especially if you're doing your first competition. You take the kernels that were published and you just play around with these kernels. Bruce was a great mentor. An applause for Bruce. Yeah, it was a great help, and yeah, every time that we had a question, we were like, Bruce, what's that? Bruce, what's the other? And every time he was very, very helpful. In this data set, there was a heavy bias to images with no zips. We saw that before. Again, it was very, very important to have a good classifier for zip no zip images. Another thing that Bruce helped a lot was to give us his GPUs, and we were able to use his computers. My computer is completely, I didn't want to say the word. I was going to say a bad word, but whatever. So thanks for that, Bruce, again. And I learned a lot. I hope Andy learned a lot.
I want to just talk about what I learned. The biggest feeling to doing this Kaggle competition, because it's vision-based, so the paper you read is mostly like in recent years, and I just feel like I spend some time set up and learn Keras and a little bit PyTorch, and then I use some existing implementation like FastCNN or look at some kernels on UNet, and then I try to figure out what is UNet and what is our FastCNN, and then the deadline is there. That's the biggest feeling. Yeah.
And thank you.
We have some time for some questions. Yes.
Thank you. So I have a question about the image augmentation. I didn't see a lot of mention of that in the different solutions. You have all these images. There's a lot of blue water in it. If there's many efforts to do the analysis and the training based on different color filters, looking for the different color spectrums and so on, adjusting contrast, which is kind of a common thing I've seen in a lot of other Kaggle competitions, to really try and pre-process the images. And the other thing was, I could have swore I saw when this competition was launched that Airbus was looking for really two competitions. One was the best result, and the other one was a performance constraint result, which I think it was a subsequent competition that they would, an evaluation they'd run on the same kernels that allowed them to see what your performance is on a short amount of time. In other words, they don't want you to have a supercomputer cluster solving this. They want to be able to, for their purposes, do this maybe in real time, maybe on satellite. So I was just wondering if there's been any mention of that, the results of the performance competition.
I didn't look very closely to the performance-based leaderboard. But one comment is that lots of top solution, they're using a classifier. They classify ships and non-ships first, and then the model. And for the performance-based solution, they usually don't use a classifier at first.
Any comment on the augmentation of changing different filters or anything?
That would be an interesting experiment. The augmentation I put into my solution is pretty simple. I think I didn't play with the color. It's basically rotation and different scales.
Generally, this is my experience. I use lots of data augmentation if I'm kind of lacking data. But in this case, they had almost 200,000 images, which is a lot. So I feel like lots of people wouldn't have done that because they had a lot of images that were available to them. Yeah.
I'd be curious how you'd say your time broke down as first-time Kagglers. So in terms of debugging and troubleshooting and reading papers and reading kernels and actually modeling and doing experiments, how would you say you spent your time?
So we have 3.5 weeks in total, and I have probably an hour every day in the last 2 weeks. And I think most of the time spent, maybe I think 50% of time spent is on reading the papers. And then, because I'm from computer science, so it's kind of easy to pick up the coding part. So I spend 50% time to read papers.
For me, it was kind of different because I come from a theoretical mathematics background. So most of my time was for reading papers and trying to figure out everything. And it was very little time on actually trying the models. At the end, I was trying to figure out, together with Adam, we were like working on FastAI and we were trying to figure out that. But again, for me, it was much more time given on theory and trying to understand that. Which I don't know if it's actually useful for competitions. Don't do that.
I just wanted to ask, you had about 5 people on your team. How were you able to coordinate, say, resources and time spent?
Well, Bruce was basically doing that. So we were meeting every 2 or 3 days, I think, online. We never actually met in person. It was all online. And we were just setting everything on his system that all of us were channeled to his system. Yeah.
So we remote log in Bruce system, which has a GPU, and I think most of my teammates, I have strong coding background, and it's a bit difficult to work as a team remotely, and I think we're not using version control. We're just using a Jupyter Notebook over the remote access.
Yeah, so just to add a little bit to that. So we, what was I going to say? So we set up a Discord server for chat, and we had a channel for the team to chat on. And everyone was on the same server, which was at my company. So there was sharing of notebooks and so on, but certainly no version control or anything like that. And there was something else I was going to say, but I can't remember now. But anyway, and then the online meetings, like just Zoom video conferencing. So we tried to do that fairly often. We talked about getting together in person, but it just never kind of worked out. Everyone had busy schedules, and with that many people, it was hard to find a time and a place to do that. So we just did it all virtually.
Yeah, I have a question about your strategies for dropping learning rates. So in particular, when and how much do you decide to drop those learning rates?
I just look at the tensor board. So after, I think, 20-something epochs, I just divide it by 2. Divide the learning rate by 2.
Yeah, thanks.
Okay, great. Sorry, please.
Just a kind of a wrap-up comment from me about the team. So this was an experiment, putting together a team like this. I offered to mentor a group of first-time Kagglers if they wanted to try it out. I thought maybe 1 or 2 people would be interested. And like there were so many people, we had to split into a couple of different competitions and teams and things. I've always claimed that one of the best ways to get into machine learning and data science is to just jump in one of these competitions, even though you feel completely unprepared, inadequate, you can't possibly do it. Just jump in the deep end anyway. And that's what they did. All these people really knew zero about machine learning or anything. And here they are standing up here talking about maskRNN and explaining it all. And I made them do all the work. I was there to answer questions. And I did try to not let just the mechanics of the competition, like how do you download the data and put it somewhere, I kind of helped with that so that wouldn't become a stumbling block. But in the space of 3 weeks, they went from 0 to what you saw tonight. So not bad.
Great. Yeah.